I don't know.
You have to know all the history of.
Seriously, yeah. The thing is, I mean, he cannot complain because he was participating.
2 years ago. Sorry, but the original is very bad.
Yeah, that's the young generation. Okay. Good. So I will announce for a while and then afterwards you just do it. Test, 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 test. Hello, 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 hello. It was a crunchy. Okay, so then welcome in the afternoon. We we now have the pleasure to I now have the pleasure to introduce to you our most booked keynote speaker, who is with the event from the beginning. So he was there as often as I was there, and it's always a greatest pleasure having Laurent, my dear colleague at IMT Atlantic in Rennes, with us. As I said already this morning, Laurent is on the mission to revolutionize the internet with a protocol that combines all the properties that would be nice to have, but with the evolvement of the internet protocols, they are not in yet. And at the same time, he is not doing a disruptive approach where you have to remove anything, everything, but it's rather an evolutionary approach. And so this is a very big thing. And I will briefly introduce Laurent before I give to his talk, which is Evolving the Internet for More Secure and Reliable Supply Chains, SHCH. And so Laurent Toutain is a professor with IMT Atlantic, and he's with the IMT Atlantic Graduate School and a co-founder and scientific advisor of Aclio, which was recently bought. And he worked for several years on IPv6 and participated in the creation of the G6 group, which has been gathering researchers and industrialists around IPv6 since 1995. His current research focuses on protocols and architectures specific to IoT's needs. From 2011 to 2015, he managed the Smart Grid Competence Center shared by Telecom Bretagne, Texas Instruments, and Itron. He is the author of several books on networks. And with that said, I hand over to you.
Thank you, Oliver. So I will present you something about SHCH. So maybe you saw it on the screen, but it's written SCHC, and even in the program I made a misspell and I put SHCH. So it's very difficult acronym to why we prefer to SHCH for static context header compression. So my goal today is not to go into the detail of SHCH and how to do that, but why it's very important for different usages. So there is measuring architecture, so like electricity meter or gas meter, where SHCH is used right now. But there is other challenge, and in the supply chain also, because you need to have interoperability to put things together. You need security, and you need energy efficiency. So all these things are covered by the SHCH protocol. So just before, if I can go to the next slide. No, cannot change it. Can you change the slide, or maybe it's not focused on? Okay, so just to give you an idea about interoperability, I show you this this stone, but last has been created 2,000 years before Christ, and as from the 21st century, what can you see? We can see that it's not something natural, it's something artificial, and there is some symbol. Nobody can understand what is written on it. But that's a fact. But if you ask to yourself, where is the information? The information is here. So we have no problem to transmit the information. For 3,000 years, this information here. The problem is that what surrounds the information, it means us, able to understand it. And that's in fact the goal of interoperability. When you receive something, to be able to understand it. To create a culture around the information, and this culture will help you to understand the message. So in computer science, so my remote control is not interoperable. So we have this this culture, and in computer science we have developed this this culture. Maybe I have to move closer to. Okay. So in computer science we create this culture, and for 30 years, or more than 30 years, maybe 50 years, we develop some protocols that now are well known and are used widely to do computer communication. It didn't appear one day and a guy say, I want this, but in fact you have some company that propose some standards. Some standards were accepted, some other standards disappear, or some standards stay for a period of time and other disappeared. And what we have right now is this architecture that makes all the computers in the world communicate and be understood, and they can be understood. So what we have this 7 layer. In fact, we have no more 7 layers, but we have at layer 1 and 2 Ethernet, Wi-Fi, 3G. Then at layer 3 we have IP, and mainly the old version, IPv4. On top of that, we have some protocol like TCP that are used to control what you are sending on the network. And now, the main application or main protocol we are using, not only to browse the internet, but also for computer exchange, is HTTP. And on top of that, you have XML. So XML is a way to represent the information, and not it's a text with some information inside, and you are able to understand things on it, follow it's a certain structure. So this way we have the interoperability for computer science. So I will not insist, if I can change, on all the stack, but something that for me is very important is the articulation between layer 2 and layer 3. In fact, in layer 2 and layer 3, we can say that you can move from one protocol to another, and it's what usually we say at school. But there is something that is more important than that. It's that if you look at IPv4, when IPv4 has been developed, do you know at which year? No. So IPv4 has been developed in 1980s. What do we use under IPv4? We use, for example, Wi-Fi. When Wi-Fi has been standardized? in the 90s. And then we have also 4G, 5G, and is more recent protocols. And so what we can see is that IPv4 was developed at a time Wi-Fi, 4G, 3G didn't exist, and we are still using IPv4, which means that we have something very, very stable at this level. And so when you build an application, if you build it on IPv4, you're sure that it will exist for a long period of time. If you build your application on a layer 2, you have absolutely no guarantee that this application will last. For example, if you have developed application directly on Token Ring, nobody will use it, even if Token Ring was very popular when IPv4 has been developed. So it means that when you want to do IoT, you want to do something that lasts for years and years, you cannot rely on a technology that will stay for a short period of time. And so IP brings this stability to the model. But the problem with IP is that it doesn't work. I think it's not IP, it's Bluetooth. But so the problem with, okay, here, so with XML, as I say, we have something that is quite related to the web, where we can have links, but we can develop more complex models. So I think it's better if I say next slide. So if you go to the next slide, you will see that XML can be used by several kind of application. One of them is XDR, RDF. So can you change the slide, please? Okay. So here, for example, you have the Web of Things. On the Web of Things, you make a lot of relation between objects, and you define a very large network of knowledge using this technology, and you can store it on an XML file. You have another thing that's very important when we talk about XML is called network management. Protocol is called, or description that is called YANG. You can describe what you have inside your system, and then you can create some XML file. So all these things has been developed by the IETF. So the IETF is a standardization organization that standards IP to HTTP. And what they've done, in fact, they did something very fantastic, interoperability for all computers on Earth, but they had only one drawback. They don't care about the energy. They don't care about how many information you are sending on the network. The IETF say we have Ethernet, we have Giga Ethernet, we have Giga Ethernet, etc. So we have a lot of bandwidth, so we don't care about the representation of information. And we can send a lot of information for that. But when IoT came, the problem is different. With IoT, we have to care about energy. So if you have the next slide. So I think even there it's okay. Here, with devices that are battery powered, it's very difficult to send a lot of things. You have to save your energy, and transmission is the most expensive thing. So people try to adapt the IETF stack to something more that spend less energy, and they develop alternative to Wi-Fi like IEEE 802.15.4. They use IPv6, and IPv6 is too large, so they develop some compression method to compress IPv6. It's called 6LoW or 6LoWPAN. HTTP is very verbose, relying on TCP, so they develop something else that is called CoAP, and is based on UDP. And it means that here you can have something that is very constrained on your device, that doesn't spend a lot of energy when you are sending information, and are quite easy to implement. And if you look, one of the beauty also of the IETF protocol is that IETF is very open, and if you don't like what IETF has developed, then you can put other protocol on it. And that's the case, for example, for DLMS. DLMS is a standard that has been developed by the energy industry and is used to connect the meters. And so we can put DLMS on top of UDP, on top of 6LoWPAN, on top of something that is look like 802.15.4. And we can have, for example, in France, we have the link key, that is a device that is in every house right now, and use this stack to send how many electricity you spend every day. And if you are not in France, then you Wi-Sun Alliance, but also do the same thing on mesh network using 802.15.4 and can connect meters. So everything is almost fine, but the problem is that the throughput is still high. It means that it's about 100 kilobits per second, and the frame you exchange is about 100 bytes. So that's why when we discover a new kind of network that was called LP1s for low power wide area networks, and if you see the constraints, is that you have some even bit per second as a network, and you have frame that can be around 10 bytes. So it's not possible to use this stack to run on these technologies. But the advantage of LP1 is that you can send a message, and this message can be received at 30 kilometers from where you send it. So it means that you have a very simple infrastructure. You cannot send a lot. So we went to IETF and say, okay, that's good. But in fact, what you have done here is not enough, and we have to create something else. And IETF, which is an American, as an American mind, is very flexible and say, okay, do it. So we create a mailing list, and then we try to, and we convince people. And 6 months after, we had created a working group that was looking on how to adapt the IP stack, IETF stack, to LP1 network. And so what we did, in fact, was to say, okay, we have a compression here that is good for IPv6, but is not enough. So what we are going to do is to generalize this compression and make some rules that are more flexible and are able to compress the whole protocol stack. And using SHCH, you can compress a stack, all this stack in 1 byte. So that's something that is very strong and is compatible with LP1 links. So on the next slide, so everybody was very excited, and everybody was very excited on LP1, and people predict, if you can go, yes, next slide, predict about 500 billion devices in 2030 connected to the internet. So what was prediction we had 10 years ago or 5 years ago? And if you look to the result, we are very, very far from this number of IoT devices connected to the internet. So on the next slide, we are trying to analyze why we don't have these 500,000 billion devices. And if we look, so I'd like to analyze this in 4 axes. One is interoperability. I always give you the definition of interoperability. It means that when you send something, you are understood. Flexibility, it means that you can adapt the network to something else. For example, you have an IP network that is used to watch Netflix movies, and when you have the COVID lockdown, then you use the network to do video conference call. And so the network can adapt itself to different usages. You have end-to-end security, which is very important because only 2 elements can exchange information and someone in the middle cannot understand it. and you have energy efficiency. So if you go to the next slide, so, the one before, so if we look at Ethernet, we have interoperability, we have flexibility, we have end-to-end security, but it's absolutely not energy efficient. If we look at some adaptation of IoT, so of Ethernet for IoT, it's a little bit better, but not that better. If we look at LP1, so next slide, if you have it. So next one. Okay. If you look at SHCH, there is no free lunch. It means that if we want to do compression, we have one factor that we have to change. And it's what SHCH is doing, in fact, is we are doing compression. We continue to have interoperability because we are talking the internet language, so everybody is able to understand it. We are energy efficient because we can have a very high compression rate. We can continue to use DTLS or any end-to-end mechanism, but we are losing flexibility. We are losing flexibility because we are going to specialize with SHCH, the internet, to do a specific task. But that's maybe a problem because internet is evolving. Protocols are evolving. So if we say something is too strict, then it will not evolve with time and will disappear. So what we introduce, it's a concept of meta-flexibility. It means that we specialize the internet, but in a way where we can describe everything very, very flexible. And it's what I will show you just after. So since I am lazy and I think you are bored with my French accent, so I will show you some two videos that are extract from a MOOC we are about to launch. We will start it in November. I have to finish some video. If you are interested, you can contact me and I will give you access. But this first video shows how you have to think about headers. And headers now, we have in mind that SHCH is changing a little bit the representation of headers. So.
As you know, protocols are an essential brick in networks. They change the nature of a link. They can, for example, be used to get a specific resource on the web, make a connection reliable, and send the information to a destination. To do that, protocols add new information to the data they transport. This information is called headers, since they are usually added before the data. The header is structured into fields. Protocols are specialized for a particular operation and stacked together to build a full communication system. For example, the IPv6 header, used to forward the packet to the right destination, is made up of several fields. When we look at the standard, they have a name, like IPv6 version or IPv6 destination address. But if we look inside the header, this name has no importance. What matters is the position. For instance, the standard imposes the header to start with a version number of 4 bits, immediately followed by a traffic class on 8 bits, and so on. But that is not always the case. For example, HTTP developed a more flexible strategy. Some fields have a specified position, such as the first line, which starts here with the method get followed by an URI, here a slash character, followed by the protocol version. All these fields are separated by space characters. The rest of the header is made up of options. They can be different from one request to the other, or even from one web browser to the other. To distinguish between the option fields, they are named. The first word before the colon is the option name. And after the colon, we find the option content. Understanding how the headers are structured is important for SHCH compression. SHCH will not work directly on the header, but on an abstract description of the header that can be generalized to any protocol fields. This is called a field description. But before we look into more details on how SHCH abstracts the
so
fields and headers,
we can
let
start
us
the
take a
video
look with
here.
Anna at the protocol we will use for the internet.
Okay, so what is important to see that we don't work with SHCH on the bits that are sent on the wire, but we reconstruct the header on something that is very, very generic. And then we can apply this compression to any protocol that exists and has been developed. So you saw that, for example, with IPv6, you have places and a field at a specific place. In HTTP or in CoAP, the place is not so important. It's the name you give to that field. And so we are able to do this generalization. So on the second video, you have the architecture of SHCH. I hope the sound will be better.
Hello, SHCH lovers! You've already seen the machine in the video generics, so let's take a closer look. As network experts, you're aware that a packet comprises one or more headers and a payload. SHCH's primary focus is header compression, leaving the payload untouched. To achieve this, our SHCH has been configured with common compression patterns observed in network traffic. The process begins with pattern identification. The header undergoes a scan, generating an abstract representation of the headers. This abstraction serves as a key to locate the most suitable compression pattern. Next, we enter the data reduction phase. Information present in the chosen pattern is removed, retaining only values that cannot be inferred from the compression pattern. This retained data is called the compression residue. A numerical identifier is then appended, indicating the compression pattern utilized. While the compressed message can be transmitted directly, there are cases where compression alone is insufficient to fit into a single frame, necessitating fragmentation. In such cases, the SHCH machine selects a fragmentation algorithm, divides the compressed message into segments, and attaches parameters. These parameters include the fragmentation algorithm's identifier and information such as the fragment's ordinal position in the original message. These fragments are then sent to their destination. On the destination, we will have reassembly and then decompression. Here we receive the last fragment, then the first. The middle fragment is missing. Now we have it. Once all fragments are received and their integrity verified, they are reassembled to form the original compressed message. The initial identifier reveals the compression pattern used, allowing the receiver to combine pattern information with compression residues, thereby reconstructing the original packet. It's evident that compression and fragmentation operate on a shared principle. An identifier dictates the methodology for compression or fragmentation and guides the correct interpretation of subsequent data. In SHCH terminology, these identifiers are designated as rule IDs, denoting either a compression or fragmentation rule. Rules are aggregated into a rule set, constituting the static context referenced in the acronym. Two critical concepts emerge. SHCH establishes a point-to-point association exclusively between two endpoints. The rule, set, or context must be identical at both endpoints. The two endpoints and their associated rules constitute a SHCH instance. As we progress, you'll witness these concepts in action through examples. Prepare for an enlightening exploration into the realm of SHCH.
So that's, of course, if you follow the MOOC. So I give you a link right now where you go to video.openshch.net. We will have access to most of the video of the MOOC, and we will open in one month. So on the next slide, this slide is very important because it represents what we saw on the video. It means that we have this instance with SHCH instance here, or SHCH element here, and we have this instance which is point-to-point. And here, for me, it's a real big in the internet architecture, because right now when you develop a protocol for, it's a worldwide protocol. So you have to take all the constraints into account to make something that works everywhere. Here it's the opposite. We are going just to work as an association between two endpoints. You can specialize the internet something specific. And here we have something with very few information that goes on the link, but we can reconstruct this information and be able to talk with every devices on the internet. And if things evolve, then we have to change the rule to make it evolve. On the next slide, we are going to see some SHCH advantages quickly. So one is about traffic reduction. It's also energy reduction, and it's very important because if, for example, you have a gas meter and you change your battery every 8 years instead of 4 years, then you spend less battery, and of course you don't have to change the battery everywhere. So you have a network that resists more, that lasts more, and that's a good point. The other point is about security, because when we specialize the internet to do something, if a hacker wants to go inside the network and attack your system, it's not possible, because here we describe which kind of traffic we want, and we cannot have other kind of traffic. So that's another advantage. And next slide. So, as I say, why is a change in the internet architecture? Because SHCH maintains the datagram concept that is very important in the internet. Each packet is processed independent of the other. But we remove the constraint to have the same packet format everywhere. And so, for example, here is an example of interoperability. You have a device that uses SHCH. It is transformed on the internet to IP protocol, and then you go back to another. You go to another network where you use another SHCH compression with the device. And so, in the future, so SHCH is something that is currently developed at so we have not finished the work. But our goal will be to publish this kind of rules for different kind of application. And you define this rule and device, and you can do the compression. What we have done also, and it can, if you want to implement SHCH, we have a lab SHCH where we have currently two stacks running SHCH. The first one is OpenSHCH. And OpenSHCH is a stack written in Python, so it's not really efficient. More to understand how SHCH works, to make some tests, to write paper over SHCH, to make measurement, and so you can have it on OpenSHCH. And the other one is the one that has been developed by Aclio, and as Mark Oliver said, Aclio has been bought by Actility, and Actility said, I'm going to release the embedded part of SHCH, and so you can implement it on all your device if you want to test it. And now on the lab SHCH, you can have access to all the stack, and so you can buy your own. Okay, next slide. So, okay, we can skip this one. And to say more about standardization, so next slide. So what we have done right now is to focus on one layer of SHCH. And it was what we expected for LP1's technology. But in fact, it was quite successful. And IETF say, okay, now you have to change your name. You are no more LP1 working group, but you are a working group. And your goal now is to spread everywhere. So it means that we can have several layers of SHCH that can be stacked together. So we don't like the name layer, because layer is what you see when you do protocols, but in fact it's not the same layer, it's not exactly the same layer. I will not go into details, so now we call them stratum, to say each layer, each stratum here compress different part of the protocol. And it can be useful on different cases. On one case we are currently studying is the usage of SHCH to send packet to Mars. So now there is some, you know that we are going to the moon, we are going to maybe to Mars one day. And so the question at the ITF now is how to the connection, how to make an IP connection to Mars and make it work. So on Friday, during the AFNIC days, you will have a Marc Blanchet, a guy that lives in Canada, that will explain why we need that, why we need standardization now for space communication, and why we need to use the same protocol as the one we use on Earth. But when you use that on very long distance and with a lot of RTTs, so times to come and go back, then you need also compression. So we are working with Marc Blanchet and others to put SHCH to other protocol, and for example, the quick protocol, that is an equivalent to TCP, that is more modern, have better flow control mechanism, can use SHCH, and we are going to work on that. Another place where SHCH can be useful, of course, Mars is a little bit science fiction, but it's a good way to about the new usage. And it's the same thing, for example, in a telecommunication system. If you look at 5G networks, you have an antenna that is in the countryside, and you have a radio link that connects this antenna to the core of a 5G core. And you have a lot of signaling messages that go from this antenna to the core, and vice versa. If you can compress these messages, you give more bandwidth for payload or useful usages. So one challenge now is to be able to introduce SHCH in protocol stacks like TCP, like QUIC, like CoAP, etc., to have also a compression, even if you have encryption be after that. Because once you have done encryption, it's not possible to do compression because you don't understand what you are sending. So it's something we are working on it right now. Next slide, please. And so the other thing, and it was my last talk, so I will not go into details. You can look at the videos from the last summer school. But we have also developed a protocol that is called CoreConf and do management on a very constrained network and very interoperable management. And we are using it to exchange rules. And this way we can set up rules automatically, and we don't have to put them on the device when the device is created. Next slide. So it can be, okay. And two last slides. One is about 4G. So we had made a lot of experiments on the narrow IoT networks, and we had very, very good performance using SHCH. We can save a lot of energy because we can do compression, but we can also play with the timers. And if you look at 4G networks, you can have some optimization at the layer. For example, at layer 2, the layer 2 of the 4G layer say, okay, I go idle. But at the same time, you have at layer 3 a message that say, I want to send it. So you go to idle, so you send a message to your network and say, okay, I'm going to sleep. And a few milliseconds after, you say, oh no, I'm wake up because I have this message to send. And you are losing, when you don't manage well all these optimization, you don't have an efficient network. So we did a good thing to optimize the network. And the other thing also we did is, for example, when you are in 4G network, you send messages, so in narrow IoT, you send a message. So when you are connected to this kind of network, you have a private address. And you leave your 4G network with a public address. So you have a NAT in the middle. But this NAT is designed to keep the context for 5 minutes. So when you are using your mobile phone, it's not you keep the same address because you have a constant traffic. When you have an IoT device that send a message every hour, then you change your IP address at every message because the context of the NAT is different. And so it's very difficult for you to authenticate the device. So what we did here is to install TLS. And with TLS, we can set up a context, a security context on your device on the application on the other side. And even if you change your address, it's not a problem because your security context is the same. So that's the kind of optimization you can have. On 5G, so we have, next slide, we have a PhD student that works on how to include SHCH inside the core network. So it's very successful. We have a very good result. And this way, we can have a device that is SHCH, but view as IP on the other side. So this is done in the French project that is Network of the Future. And 6G, there is also people that are interested in SHCH for another reason. Is what they call ambient IoT, and is a kind of NFC using a 6G network. So it means that your device will be powered by the network radiation. So you send, you know that you have MIMO, you get beamforming, so you can send a beam device, so you power it. So the device will take energy from the signal, and then we'll be able to send a modulation. But of course, the throughput is very, very limited. And so your device has, for receiving something, your device has to stay connected a long time and is not compatible with a network that cannot maintain all these states. So SHCH is a good solution to solve this problem. So next slide, please. So here we have also work on LP1. I talked at the beginning, but I will go into details. Next slide. So if you are interested by SHCH, we have this course on Coursera that will be open in 1 month. If you are interested, send me a mail or talk to me. I will be here until Friday, and I can give you access to this class. We have the book of SHCH that is also linked to this class. And we have a virtual machine where you can make some exercise using OpenSHCH. Next slide. So here is the book of SHCH. Okay, so that's a long road about, you know, V6, IPv6 has been developed in 90s, and we are now using it. So when you install something in network, it takes a very long time, because you have a lot of devices, and you have to make all these devices evolve at the same time to be able to push that. So SHCH is something that started 8 years ago, as I say, with LP1. Right now, what we have done is already a deployment of a gas meter in Italy. We have about 7 million gas meters that will use the SHCH technology. You have also in Brazil, in Africa, where they are using this technology. We are targeting mobile vehicle to exchange information. And now our goal also is to target some other standardization organism like 3GPP, who is working on SHCH, and we have also the Wi-Fi Alliance, also interesting because what? That's over. So if you have questions. Yeah.
Maybe a very detailed question about devices you showed earlier, where you said the one device is in every French household now.
Mm.
They get batteries, so they're very.
No, because it's electricity meter.
Okay.
So they have no real constraint on energy. But since you have billions of this in a network, so you have to take care, because otherwise a lot of energy will be consumed. But you don't have this constraint on energy. It's more on transmission because they use power line, and so you have a limited throughput for them. But for gas or electricity, here you have a problem of energy. Okay, yeah. Mm. Okay, yeah. Mm. Mm. So that's I don't know if we change the world, but uh, in fact the idea at the beginning is that history is repeating. It means that look at IP becomes big, that it becomes an attractor, and everything goes to IP. So you have at the beginning IP just to exchange file, then you use IP to exchange pictures, then you use IP to exchange videos, and then you have videos on IP. So now watch TV, it's on IP. If you make call, it's on IP. So everything goes to IP. So it's an attractor of all the services because we need interoperability. It's the beauty of interoperability. It means that you develop only one single network and you have all the usage. So the costs are limited. So that's, and we got this technology from in RAN, so we have LoRaWAN network, and they say no, we are going to use it as a layer 2, and we are building our application directly on layer 2. And it's very easy when you want to make proof of you develop a few lines of codes and it's okay. But you just look at one, it works at time, but in the future it will be very difficult to make it evolve. As I say, the stability of protocol at layer 2 is not that high because you have new technology. We are in a French-German school, so in France we have LoRaWAN because it's American technology, but it comes from a lab in Grenoble in France. In Germany you have IoT, which equivalent, but it's different technology. Which one is the best? I don't know. But it means that when you are someone that decide what do I do, so you are a CEO of a company and say, do I use LoRaWAN? Do I use IoT? Which one will succeed and will be the only technology that will survive? You cannot guess. So you block everything. If you say it's on IP, because you know that IP is stable. At least now. 10 years ago or 20 years ago, it was not that case. But now, if you say to someone, I want to use IP, then you have no problem to convince people to go on that technology. And so that was the first idea, that we'll go to IP. Of course, the problem was that IP is big and it doesn't work, so that's why we developed the compression and fragmentation mechanism. So that's mainly the way to go there. And so we develop things, and then we start analyzing what we have done, and we say, oh, it's not so bad because, for example, we don't break the datagram mechanism, the datagram concept. And we didn't have that in mind at the beginning. And in fact, if you look at other compression mechanism, they create a flow, and then they compress on that flow. It means that if you lose a packet in the middle of your flow, you have to reconstruct everything. Here, if you lose a packet with SHCH, you lose a packet. That's all. And the rest continue to work. And so there is this nice property that says that we are not just a way to compress things, but we are a new way for the internet to evolve. So maybe we are stupid or they will not exist. But we have this need for flexibility in the internet that we didn't have. And just to make some commercial for Friday, so it's a limit of the internet. You know that we had the Olympic game in this summer, and so we tried to make the same thing for internet, and so our internet can go faster, nearer, smaller, etc. So see different alternatives, the space, underwater. If you have no more energy, how you can continue to make an. So that's some possible evolutions. So I don't know what, I think it's difficult all the time, because when you are alone and you have your ID, you have to convince people, and so it's not so easy. And then you have convinced people, they are not going in your direction, so you have to force them to go to there, or you have to accept what they did. So you have always some challenge when you do things. No, what was very important is that we it was in the Yokohama meeting in so 7 years ago, and Alex Peloff and Anna Minaburo came to this meeting. They met people from IETF and say, oh, there is a new technology you are ignoring, it's LP1, you see, you have this limitation and limitation, so we would like to create a group. And they say, no, you are not, you are stupid friend guy, that go is our very clever guys from America, and we don't care about what you say. They say, it was totally the opposite. Okay, prove it, do it. And so they, as I say, they ask us to create the mailing list. We create the mailing list, and then we convince people. We had 3 months after another meeting in Buenos Aires, where we proposed some evolution to the technology. So we had to look to what exists and say, no, there is a gap. Nobody at the IETF can fill this gap, so you have to create a new working group on that. And IETF say, okay, but now we don't standard just for fun of doing standard. We need application. And so 3 months after, we had an involvement from LoRaWAN, Sigfox, IEEE, and 3GPP. And IETF say, okay, go do it. And so it's something that is very open in standardization. That doesn't exist everywhere, because IETF is something that is very flexible and adapts to new technology. And I think that it's very important, because if we had this technology just proposed by IMT Atlantic, it's not interoperable. It's a stuff from IMT Atlantic. If it's RFC 8724, this is interoperability, because it's something that can be used by a lot of people. So standard is very important for this kind of things.
And when did you get the standard? 2 years ago, something like that?
I don't remember. It's 5 years
it was
ago.
already at my time at IMT, I guess.
Yeah,
So
you have to read it, but it was very different. 3 or 5 years ago.
Okay. So super exciting. Do we have more questions? Yes.
So you can compress everything if you want. It depends really of what you are sending on your device. If you have something that is very, very repetitive, and you have nothing to guess, because you predict everything, then you can have a very high level of compression. So when you have an electricity meter, then it's always very, very repetitive, so you can compress a lot. If you have something that is more flexible, and what we say, SHCH to the moon, or all these things where you will have different kind of application, then here you cannot have the same level of compression. What we plan to do is, using management, is when you discover a pattern that is really used frequently, then you create a rule for that pattern. And then you can use a higher level of compression. But of course, creating a rule, it costs bits and bytes. So you need to have a trade-off when I do it, when I don't do it. So it's some studies we have to do right now. So we are, I say, for example, when usage with co-op is 1 byte. So you can compress IP, UDP, and co-op in 1 byte. So it's for a specific example. So in the MOOC, you have 2 examples. One is a scenario where you have a device that sends periodically messages. And so here you can compress to 1 byte. And the other one is the underwater scenario, where you have a boat that arrives on an area and queries some underwater sensors. And you have different rules, but you have almost the same result. But if you put security encryption, it's a little bit more.
Okay, cool. Then I would say let's thank you once again.
Yeah, I saw that, but it was not so easy. It didn't work.